So next we're going to talk about operations with the derivative, like we could factor constants out from the derivative, or we could distribute derivatives through addition or subtraction signs. So the first operation is the constants could be factored out of the derivative. So if I have the derivative of a constant multiplied by a function, I can factor the constant out such that I could first take the derivative of the function, and then after I do that, then I could multiply it by the constant. So that's pretty convenient. So now we're going to compute the derivatives of these functions. First is the derivative of 5x cubed, the next one's the derivative of e to the x plus 7, the third is the derivative of negative 3 cosine of x, and the final one is the derivative of the square root of 2 over x. So I urge you to please pause the video and try them before continuing on with the video. So the first one is pretty straightforward, the derivative of 5x cubed. You just factor out the 5, you have the derivative of x cubed, and then you could use the power rule. You have 5 times 3x squared, which is equal to 15x squared. So for the next problem, it requires a little bit more manipulation, but it's still the same idea. So we have the derivative of e to the x plus 7, and notice how we could rewrite it as the derivative of e to the x times e to the 7th. We could factor out the e to the 7th. So we have e to the 7th times the derivative of e to the x. The derivative of e to the x is itself, so we have e to the 7th times e to the x, and we end up with the same thing, e to the x plus 7. And notice how even though we might have to know some algebra rules or how to manipulate exponents or different types of functions, it's still the same idea. All we're doing is just factoring out the e to the 7th and taking the derivative. The next one, we have the derivative of negative 3 cosine of x. We can also factor out negative constants. So we have negative 3 times the derivative of cosine of x, which is negative sine of x. So we have negative 3 times negative sine of x, which is 3 times sine of x. So for the final one, it may look a bit different, but the same process applies. So we could first factor out the square root of 2. So we have the derivative of the square root of 2 times the square root of 1 over x. And then we could distribute the square root over the numerator and denominator. So we have the square root of 1 divided by the square root of x. The square root of 1 is 1, and we have the square root of x in the denominator. So we have the square root of 2 times the derivative of the square root of 1 over the square root of x. Now 1 over the square root of x is nothing but x to the negative 1/2. So we have the square root of 2 times the derivative of x to the negative 1/2. We could use the power rule, subtract 1 from the exponent. And we have square root of 2 times negative 1/2 times x to the negative 3/2. And finally, we could just combine the square root of 2 and the negative 1/2. And we end up with negative square root of 2 over 2 times x to the negative 3/2. And the last problem, it might look a bit intimidating initially. You have the square root covering this fraction, but remember your functions and remember how you can manipulate them, because it'll make it a lot easier. So then we're going to be looking at what happens if we take a derivative of a sum. And what you could actually do is you could distribute the derivative to each function individually. So if I have the derivative of f of x plus or minus g of x, then that's the same thing as taking the derivative of f of x, then taking the derivative of g of x, and then adding it together or subtracting it. And this is very helpful because it allows you to take a very complicated function and break it down, allowing you to differentiate it more easily. So I have 4 functions, and I'm going to give you a couple seconds to try and find the derivatives of these 4 functions. And yeah, hit pause if you need more time and continue when you're ready. So let's start with the first problem. We have the derivative of 1 over square root of 7x plus square root of 3x. And notice that the first thing that we could do is we could factor out 1 over square root of 7 and square root of 3 and the other term. So we have the derivative of 1 over square root of 7 times 1 over square root of x plus the square root of 3 times square root of x. And this is very useful because in the third step, you could factor out the 1 over square root of 7 and the square root of 3, and it allows you to factor the constants and take the derivative more easily. So the next thing we could do is we could then distribute the derivative, and you could see how this, complicated function, the 1 over square root of 7x plus the square root of 3x, it's broken down into a lot more simpler derivatives because we're allowed to use this rule. So we have the derivative of 1 over square root of 7 times 1 over square root of x plus the derivative of square root of 3 times the square root of x. So from there, we could then factor out the constants and we could rewrite it in power form. So we have 1 over square root of 7 times the derivative of x to the negative 1/2 plus square root of 3 times derivative of x to the 1/2 We could then take the derivatives by using the power rule. So we have negative 1/2 x to the negative 3/2 and 1/2 x to the negative 1/2. And finally, all we need to do is just combine the constants. So we just have negative 1 over 2 times square root of 7x to the negative 3/2 plus square root of 3 over 2 times x to the negative 1/2. So notice that I didn't rationalize the denominator for negative 1 over 2 times square root of 7. And that is totally fine. Once again, if you're taking like AP Calc BC or something, you know, you might not have enough time to rationalize the denominator. There's a lot of things you need to do. So that's totally fine if you didn't rationalize the denominator. So now we have the derivative of 7x to the fifth plus 4 times square root of x all over 9x squared. And it looks a bit different because we have a rational function. But remember, we can manipulate this algebraically to make the differentiation more easier. So what we could do is we see this 9x squared term, we could distribute that to the two terms in the numerator. So we have 7x fifth over 9x squared plus 4 times square root of x over 9x squared. Now notice that I factored out the 9 in the denominator since it's a constant. So I have the derivative of 7 over 9 times x to the fifth divided by x squared plus 4 over 9 times the derivative of x to 1/2 over x squared. And notice how I rewrote the square root of x as x to 1/2. And from there you could just use exponent rules. So x to the fifth divided by x squared as x cubed. So you have 7 over 9 x cubed. And then you add that with 4 over 9 and you see that we have x to 1/2 divided by x squared. So we do 1/2 minus 2, that's x to the negative 3/2. So we have plus 4 over 9 times x to the negative 3/2. So from there, the next thing we could do is we could then notice that how we have two terms. We could distribute the derivative to each of those terms. So we have the derivative of 7/9 times x cubed plus the derivative of 4/9 times x to the negative 3/2. Now notice that we have 7/9 and 4/9, and we could factor those two things out. So we have 7/9 times the derivative of x cubed plus 4/9 times the derivative of x to the negative 3/2. So now we could just use the power rule and we could just subtract 1 from the exponent and we have 7/9 times 3x squared plus 4/9 times 3/2 times x to the negative 5/2, not 5/2, negative 5/2. And as a result, we have 7/3 times x squared minus 2/3 times x to the negative 5/2, and that's our final answer. So for the third problem, you have the derivative of 5x to the fourth minus 3x squared plus 9x plus 10 over 3. And notice that this is just a traditional polynomial, and at this point, you can take the derivatives of all polynomials. And all you gotta do is you just gotta distribute the derivative. So you have the derivative of 5x to the fourth minus the derivative of 3x squared plus the derivative of 9x plus the derivative of 10/3. We could factor out the constants, 5, 3, I already factored out the negative 1 in the second term, plus 9, we could factor out the 9 in the third term, and there's nothing to factor out for the last one, it's just a constant. So then we could just use the power rule. We have 5 times 4x cubed minus 3 times 2x plus 9 plus 0, 9 times 1. And finally, when we combine the constants, we end up with 20x cubed minus 6x plus 9. And the amount of steps might vary for you. For instance, like you might not need to write the derivative of 5x to the fourth minus the derivative of 3x squared plus the derivative of 9x. You might go straight to the second to last step, 5 times 4x cubed minus 3 times 2x plus 9 times 1. So it shows how the number of steps might vary. And you know, when you go and learn more and more calculus, at one point you might be looking at this just, alright, f of x equals 5x to the fourth minus 3x squared plus 9x plus 10/3, and right away you could apply the power rule and you'll know that it's 20x cubed minus 6x plus 9 without doing any steps. So it can vary and it can take time to master the skill. And finally, we have the derivative of 4e to the x minus 3x squared plus 5/2 times sine of x. We do the same things we've always been doing. We go distribute the derivatives, we factor out the constants. We have 4 times the derivative of e to the x minus 3 times the derivative of x squared plus 5/2 times the derivative of sine of x. The derivative of e to the x itself, the derivative of x squared is 2x, and the derivative of sine of x is cosine of x. And from there, we could go and combine the terms. We end up with 4e to the x minus 6x plus 5/2 times cosine of x. So attached to this video is a PowerPoint with more examples that you could look more into. And One example is to find the equation of a tangent line at a point for a curve, and we've been differentiating so many different types of functions, exponential, sinusoidal, rational, radical, polynomials, that it's easy to forget what we're actually doing when we're taking the derivative, in which we're trying to find the slope of the tangent line for a point in the curve, or in other words, how we're trying to figure out how fast the curve changes at a point. And examples like these would help reinstate these ideas. Other examples may be practicing calculating higher order derivatives, or noticing patterns and writing expressions, or just calculating harder derivatives. And that's all for this video. Next video, we're going to be learning how to take derivatives of product. If you have two functions multiplied together, how will you take the derivative of that? All right, see you then.